Suppose an observed series moves around an unobserved level that itself changes gradually over time. We want to estimate the current level as each new observation arrives. The local level model is the simplest setting for this problem. It contains only one latent state, yet it reveals the central logic of the Kalman filter. Every update balances a model-based prediction against the information carried by a noisy new measurement. The state equation says that the level at time t plus 1 equals the level at time t plus a state innovation called eta. Eta has mean 0 and variance q. The observation equation says that y at time t equals the current level plus measurement noise called omega. Omega has mean 0 and variance r. The two disturbances are independent, so q and r describe distinct kinds of uncertainty. Variance q measures how much the latent level can genuinely move between dates. Variance r measures how noisy each observation is around that level. A large q allows rapid state evolution. A large r says that individual measurements are unreliable. Only their relative magnitudes determine how aggressively the filter reacts. Treating both variances as generic error terms would miss the economic distinction that drives the recursion. The Kalman filter follows from conditional moments of jointly normal variables. For jointly normal quantities, the conditional mean equals the prior mean plus a covariance-weighted surprise. The conditional variance equals the prior variance minus the uncertainty resolved by the observation. In the local level model, these familiar conditional normal formulas become a prediction step and an update step that can be repeated one observation at a time. Before observing y at time t, let alpha at t given t minus 1 denote the predicted level. Let p at t given t minus 1 denote its predicted variance. These two numbers summarize everything in the past data that matters for the current state under the model. This compression is what makes the algorithm recursive. We do not need to re-estimate the entire history whenever a new observation arrives. The one-step forecast error, also called the innovation, is the observed y at time t minus the predicted level. It measures how surprising the new observation is relative to the model. Its variance, called v at t, equals the predicted state variance plus the measurement variance r. A large surprise is not automatically important. Its interpretation depends on how much variation the model expected in advance. The Kalman gain at time t equals the predicted state variance divided by the forecast error variance. It lies between 0 and 1 in this scalar model. The updated level equals the predicted level plus the Kalman gain times the forecast error. The updated variance equals 1 minus the gain, multiplied by the predicted variance. The observation changes both the point estimate and our uncertainty about that estimate. After updating, the filter predicts the next level. Because the local level follows a random walk, the predicted level for time t plus 1 equals the current updated level. The predicted variance for time t plus 1 equals the updated variance plus q. The addition of q is essential. Even after learning about the current state, a new state innovation creates fresh uncertainty before the next observation arrives. Combining the update and prediction gives one compact recursion. Compute the forecast error. Add predicted state uncertainty and measurement uncertainty to obtain its variance. Form the gain. Correct the predicted state by the gain-weighted surprise. Reduce uncertainty because an observation has arrived, then add Q because the state evolves. Repeating these steps produces a real-time estimate and a sequence of one-step forecast errors. The gain has an intuitive signal extraction interpretation. When R is large, the observation is noisy, so the gain is small and the estimate stays close to the model prediction. When predicted state uncertainty is large relative to R, the gain is large and the estimate moves toward the observation. A common mistake is to describe a large gain as universally good. It simply reflects the model's relative uncertainty. The update can also be derived from the joint conditional distribution of the state and the forecast error. Their covariance equals the predicted state variance because the state is the common source of uncertainty. Dividing this covariance by the forecast error variance gives the Kalman gain. Gaussian conditioning then yields the updated mean and variance. This derivation explains why the same covariance weighting appears in more general multivariate filters. Let me separate three things that are easy to confuse. Take two observations with the same raw forecast error. Dividing each by the square root of its forecast error variance tells us which one is more surprising in a statistical sense. The change we actually make to the state is different again. It equals the Kalman gain times the error. So it is large when the state is uncertain relative to measurement noise and small when noise dominates. Raw error, standardized surprise, and state update are three related but distinct answers. Under the correctly specified linear Gaussian model, one-step forecast errors are independent Gaussian variables with their own predicted variances. A lower triangular transformation maps the original correlated observations into these innovations. In matrix terms, the Kalman filter provides a Cholesky-type decomposition of the covariance matrix of the data. This property supports efficient likelihood evaluation and offers diagnostic residuals that should be approximately uncorrelated. Let me trace how the error itself evolves. The state prediction error is simply the true latent level minus our prediction of it. The observation forecast error is that state error plus measurement noise. Now look at the next period. Its state error keeps only the part of the old error we did not correct, then adds a fresh state innovation and subtracts the gain-weighted measurement noise. So the recursion shows us, step by step, how filtering both carries uncertainty forward and corrects it. Initialization supplies the first predicted state, mean and variance. An informed prior can use substantive knowledge. A diffuse initialization uses a very large variance when little is known. With a diffuse prior, the first observation receives nearly full weight. The influence of initialization often fades as data accumulate, but it can matter near the beginning of short samples. Extremely large numerical variances can also create computational instability. The ratio of process variance to measurement variance governs the filter's practical behavior. When process variation is large, the state is allowed to move quickly, and the gain gives new observations substantial weight. When measurement variation is large, individual observations are treated as noisy, and updates are restrained. Estimating this ratio poorly can make a true signal look erratic, or make a changing state look artificially smooth. The local level filter is optimal for the stated linear Gaussian model, not for every time series that appears smooth. Outliers, structural breaks, heavy tails, or a misspecified ratio of Q to R can produce misleading estimates. Diagnostics should examine standardized innovations and sensitivity to the variance parameters and initial conditions. The method is powerful because its assumptions are explicit, not because it eliminates the need for model checking.